All right. So I've talked about an electric field calculation where you just take the charge divided by the distance squared times 9 billion. Then if I want to figure out the force, which is the much more common problem, you're going to take the two charges times each other times 9 billion and divide by the distance squared. And then this last one, which is a potential. Potential is just force times distance, and since there's a distance term in the bottom, you're going to get one of those to cancel out. So the potential energy, especially the change in potential energy, which is what it's asking for, how much does the potential energy change, is equal to the 9 billion, okay, times the two charges, over now just one distance, not distance squared, because force, which is what this calculation is, which would be squared times distance, one of those is going to go away. All right, so let's change that. I'm going to change these numbers to the actual versions. All right, so we've got, now these are nanocoulombs. Nanocoulombs is the billionth. So that's 10 to the minus 9. So we're going to get times 1, and it's a positive, times 10 to the minus 9th coulombs, times a minus 5 times 10 to the minus 9th coulombs, all divided by the distance between these two. The distance is going to be the change in distance, okay, from 5 meters to 1, but it's going from 5 meters, that's the initial, going to, which is 1, so it's always phi. Let's go this way. I'm going to remind you by writing this minus phi. So the final distance is 1 meter, minus the initial distance, which is 5 meters. Okay, that's going to become important because it changes these signs, and that sign is going to be interesting. So 1 minus 5 ends up becoming, well, let's work that out. Okay, first I'm going to just take the tops times each other, and you're getting the hang of this. You take 9 times 1 times 5, and it's going to be the opposite of that. So 9 times 1 is 9. 9 times 5 is 45. Okay? 45, those two times each other. Now I'm going to take 10 to the 9th, and I'm going to subtract a minus 9. 9 minus a minus 9. Sorry, these are multiplied. So 9 plus a minus 9, so that's going to be 0. 9 plus a minus 9 is 0. And then another minus 9, so that's going to be minus 9. So 45 times 10 to the minus 9. And then the bottom has got to be 1 minus 5, which ends up becoming a minus 4. And this has got a minus in it too. So you got two minuses. Okay? These are opposite charged particles. As they get closer, they're going to become lower in potential energy. I'm going to make sure that's right. Everything's plus minus and final minus initial. Okay. Now, let's just finish this out. 45 divided by 4 is roughly 11.2 times 10 to the 9th. And the unit that I'm going to get, let me write those in, Newton meters squared divided by Coulomb squared. Okay. This is going to be 1 of the meters down here. That leaves 1 of the meters up top. Coulombs cancels out, so I got Newton times meters. Potential energy. Yeah, force times distance is in joules. Newton times meters is now in joules. Okay, 11.2 times 10 to the minus 9th. It's positive, so how much did it change? It changed by 11.2. And again, I'm always tricky about this, but I'm getting closer to two opposite charged particles. If they're getting closer, that's lower in energy. It's like going downhill. You went from the lower amount to even lower. If you went the way you went naturally, you're getting lower in energy. So this is actually 11. The potential energy change is 11.2 times 10 to the minus, or 11.2 nanojoules lower in energy. You just got to kind of think about what just happened. We got closer with opposite charged particles. So if that helps you to do those kinds of problems, we're going to give you a couple of each of those kinds here in the worksheet today.